explain, sir? Can I repeat again?
Sure. Uh, these are stranded conductors, the yellow one you can see here. These are placed in a stator slots, and similarly, it is placed in all the stator slots. So in this geometry here, it is 48 slots and 8 poles, right? So in 48 slots, all of 48 slots, copper winding, copper in the form of a stranded wires, they are placed among a stator slots, all of the stator slots. So, and they will combinedly create number of turns, and that will create MMF, which will link to rotor MMF, and hence the torque will be produced. So this is for armature winding, and this is for field winding. So you can see this how this
Sir,
field.
small doubt, sir.
Yeah, please go on.
Sir, MMF అంటే ఏంటి సార్?
Sorry, MMF.
MMS F అంటే ఏంటి సార్ MMF?
Sorry, I am not able to hear you properly. Uh, yeah, I
Sir,
heard
MMF,
MMF.
which meaning, sir?
Magnetomotive force, MMF. Stator creates MMF. MMF is equal to
Okay,
number of ampere turns, NI.
okay, sir. Okay, sir.
हाँ. So that is MMF. Uh, so this is how all the conductors will be placed in all other slots. Here only two sides of one rotor poles has been shown where conductors are placed in a stranded manner. So this is called a stranded manner. Okay. Here either you can do a stranded winding or you can do, single rotor bars, single copper bars. Uh, so why do we do in a stranded manner? Does anyone has any idea? Why don't we put one single thick copper wire in the slots and we do our work?
Skin effect, sir.
A skin effect, yeah, very correct, Anubhav. So it is due to a skin effect, and also it reduces proximity effect due to the interaction between a stator copper bars and rotor copper bars. So they induce their own EMF when rotor starts rotating. Okay. So this is how a typical wound field synchronous motor looks like, and it is this motor can also be considered for any electric vehicle applications. Okay, although people do not use it frequently due to the complications of brushes and commutators. And you would have heard that there are so many nowadays advanced motors which does not require any commutators and brushes. They are called as well brushless or brushless AC or brushless DC motors. So they are they are very efficient in removing of your commutators and brushes. So this motor is employed in some of very premium electric vehicle, very costly motor, very costly electric vehicle. Do you know which vehicle company is that who had employed wound field synchronous motor in their vehicle?
Tesla, maybe?
Tesla is using, you know, and they used to use induction motor earlier, but now they shifted to IPM, interior permanent magnet synchronous motors.
Yes,
So
I read about it in an article.
yeah. So that is very interesting things if you track all those things. So they employed, interior permanent magnet synchronous motors. The last day I was discussing, they can produce reluctance torque as well as electromagnetic torque. So both the advantages they can achieve. And in electric vehicle applications, let me show you. Field weakening operation is very challenging. If you need to run any electric vehicle above base speed, so field weakening we must need to do because our constant torque capability is depending upon the what is the voltage limit, and after that it is operate in field weakening. So this is field weakening mode, and this is here constant torque. So this is the typical characteristics of motor which employed in any EV. And fortunately, the EV motor requirement is also this one, this curve. So uh, it is very fortunate that whatever the requirement of electric vehicle that matches with electric motors. So that is very big advantage with electric motors. So that's why people focuses more on advanced electric motors, which can provide so higher efficiency of more than 95%. Whereas the earlier nowadays, whatever conventional engines that is based on fuel, petrol engines, we also call them in technical language internal combustion engines. So internal combustion engines cannot give you efficiency higher than 40%. So uh, this internal combustion engines had efficiency of less than 40%, while your EV motors can give you efficiency of above 90%. Even induction motor as well, they can also give you efficiency around 90%, and some advanced rare earth permanent magnet motors PMSM, they can give you efficiency more than 95%. So which is very attractive feature of electric motors. So this is one thing. So I was asking which vehicle employed wound field synchronous motors, which we use traditionally. So Nokirti said Tesla, but yeah, Tesla used IPM. So any other guess? I will give you one hint. It costs around 80 lakh rupees. That vehicle costs around 80 lakh rupees. So which vehicle could be?
Audi.
No, you are there, but it is not Audi. It is similar to that community.
BMW.
Yeah, BMW, correct. So BMW has employed this motor. Why they employed this motor? Although this motor needs maintenance and all, but one drawback with permanent magnet motors is we cannot control field because field is produced by permanent magnets. And to demagnetize this or to do field weakening operation, let me open this tab. So for field weakening operation, let us see, this is permanent magnet, okay? So they are producing fluxes and linking to a status. And during field weakening, we need to demagnetize it in this direction. For that purpose, we need higher amount of a stator current because this is like a strong field. These are the strong fields. Strong fields. To demagnetize or to operate at above base speed, we need higher current, which will lead to higher losses, as well as permanent magnet has a temperature issue. If current will increase, the temperature will also increase, and that will demagnetize the magnet. And once permanent magnet demagnetizes, it is very difficult to restore back. So that's the purpose. And second purpose, rare earth permanent magnet in extraction of rare earth magnets, it produces so many minerals, like very high amount of minerals. So we come again back to a square. Again, the IC was producing some pollutions, and after that, we shifted to EV for clean energy, and for EV we extracted PMs. PMs again created pollution. Means in extraction of minerals, so that will pollute all our surroundings. So we come back to a square. So for that purpose, many premium vehicles and premium companies are taking such initiatives to avoid permanent magnets. So that is another issue. I distracted from the topic. So I was discussing about this motor. So let me show you some flux path. So this is how flux flow in the motor. I hope you are able to visualize it, how fluxes are flowing. So let me take a snap of this so that I can explain. So this is kind of flux, you know. Uh, it is entering from north and leaving from the south. So this complete loop is made here. And in similar fashion, the stator MMF will rotate and hence the rotor will rotate to catch up the stator MMF. You see this animation? I hope you are able to see the animation. Here the stator MMF is rotating and the rotor is trying to catch the stator MMF through the minimum reluctance path. So this will be your, D axis and this will be Q axis. Let me denote here. So this will be your D axis. You know D axis? Which axis is known as D axis? Can anybody let me know?
Minimum reluctance.
Minimum reluctance path. Fine. So this is D axis, this is Q axis. So there will be difference between D and Q axis. So that difference creates reluctance torque. So the difference between LD minus LQ is responsible to create a reluctance path because this rotor is trying to align itself along the minimum reluctance path to the stator. And it is crossing this air gap. So this is air gap. Let me show you. So this air gap is very thin. If you will see, the air gap would be around 0.4, 0.5, right? Here it is 1 mm. Maximum it can go up to 1 mm. But generally people build with 0.5 mm, 0.8 mm. Okay, so 1 mm air gap is even considered as large air gap. So this was about it. So any question in this?
No, sir.
Okay, fine. So these are how sinusoidal back EMF will be generated. So you have you have learned or you have mugged up like it creates sinusoidal back EMF. So this is how it is not pure sinusoidal. It will have some THD distortion in its waveform. So this is kind of back EMF will be generated, and this is how torque will be generated. So you can see there will be some ripple. We cannot get pure torque, a smooth. So this is one thing. Many people do research in reducing this component. Yeah. So this is how your air gap flux density varies. Right? It is also expected to be sinusoidal. Not this one, this one. So this is also expected to be sinusoidal, but there are stators and rotor tooths. So they in pure cylindrical machines and slotless machine not slotless, toothless machine. In toothless machine, there will be pure sinusoidal, but here air gap is not uniform, so you would not get uniform air gap flux density. So this is how flux linkage looks like, how fluxes are linking between a stator and rotor. So, and currents are sinusoidal and inject sinusoidal current. And then after all these things, you will get this kind of flux. So I hope it is all about this machine. I hope you would be able to visualize the machine. Let me show you some 3D animations also so that you would be able to see where all the components are. So this is a typical salient pole rotor in 3D. Okay, so you've seen 2D mode. So how it is protruding across axial length. So this is how rotor poles look like. And if you wound it with windings, so this is how typical. If you get time, you search BMW fifth generation e-drive. Okay, so you will get some YouTube videos where they have shown some part of salient pole rotor. So they have also used, I guess, 8 poles. So this kind of structures you would be able to see in their motor drives. And in BMW iX3, I guess, or or they have employed this motor. That's one thing, and let me show you a stator, how stators are connected with windings. Okay, so this is how the end windings looks like, and this is the separator. Uh, how each rotor poles are separated from the other poles, so that there would not any short circuit. So this is a typical wound field synchronous motors, which you study and you get thorough with it. Okay? So I guess that's all about it. So let me go and solve some problems. Not on synchronous motors because I have already solved so much problems on synchronous motors. So I have today two problems, one based on DC motor and one based on transformer based questions. And some other day I will try to show you some DC motor as well because it is a kind of complicated, a bit complicated. Why? Because here armatures are placed on rotor. So when armatures are placed on rotor, so there would be brushes and commutators would come. So that I will also try to show you. So let me move ahead with problems. So in this problem, it is saying that armature voltage of 100 volt. Armature voltage means terminal voltage, that is 100 volt at rated field winding voltage, right? Why rated? To operate in constant torque region, we always need rated flux, right? In field weakening region, we reduce the flux, but flux cannot go beyond rated because the reason behind is one is saturation, and other it will take lot of current, so that our efficiency would drops. So flux is equal to phi rated. A speed is given 1000 rpm, and it is driving a fan. So it is a fan kind of load, and fan kind of load has some torque speed characteristics. So its load is proportional to the square of the rotor speed. Okay, so load torque is proportional.
ਹਾਂਜੀ ਭਾਈ ਪਾਣੀ ਇਹ ਠੰਡਾ ਹੋਈ ਜਾਣਾ ਥੋੜਾ ਮੈਂ ਤਾਂ ਰੱਖਿਆ
Yeah, no, Kirti, you are trying to ask
ਹਾਂਜੀ
anything?
ਹਾਂਜੀ ਪੁੱਛ
I think you are unmuted by mistake, I guess. I am muting yourself. Okay, so so load torque is depending on speed of your rotor, and generally in from machine side, if you see, this is the requirement of load. This much torque the motor should be capable of delivering, but machine torque depends on current, right? Current and flux. So armature current and flux, right? So this is the characteristics when both field MMF and armature MMF is 90 degree, then torque is maximum. So this torque is depending on this electromagnetic torque, which will be produced by motor. So that depending on armature current and flux. And here the load torque is dependence of rotor speed square, and we need to find what will be the value of armature voltage, which will reduce the rotor speed to 500 rpm. So earlier rotor was running at 1000 rpm. Let me call it speed 1, N1. Now we need to reduce the speed of motor to 500 rpm. So how we can do? We all know the speed is dependence of back EMF. Whenever a speed term will come, you can see speed depends on back EMF as well as back EMF depends on flux. So we have some constant, common constant. We know K phi omega. This is a very famous formula, and torque is equal to K phi IA. So torque dependence on flux and current, back EMF or induced EMF dependence on flux and speed. Okay. So first, initially speed was 1000 RPM. Now we need to reduce it to 500 RPM. What kind of flux or current or what kind of voltage will be there so that this speed will be reduced to 500 volt, 500 RPM level. So first, what we will do, we will calculate what was back EMF in first case. Earlier, what was the back EMF? So we all know it is a separately excited motor. It is mentioned explicitly. It is separately excited DC motor.
Excuse me, sir.
Yeah, please.
Sir, armature voltage should be equal to the back EMF.
How? Why?
I think.
Why you are saying
Sir,
so?
sir, armature voltage is the voltage appearing across the armature, and
Okay.
terminal voltage is the voltage which is applied across it.
Okay.
So yeah, in between a resistance is coming, na? Then why you took the armature voltage as terminal voltage?
Yeah, I will explain it. So whenever we mention armature voltage, we mean by how much voltage you are applying, right? You cannot apply this voltage because this is motor, so this will be developed. You cannot apply this voltage, this back EMF, right? This you are calling, this you are saying that I should call it armature voltage, right? Whatever this voltage would be, armature voltage. But this is
Yes,
not the case. I will explain why. So there will be some RA. Okay. This is terminal voltage, and since it is motor, so current will draw from the supply. So as you know, in motor or even in generator, in motor you have control on how much supply you give. You know electrical input, mechanical output. Okay. So how much voltage you are supplying, that will come across the armature. So that's why we call it armature voltage, right? This is also the part of armature, right? So whatever the voltage you apply across the motor or armature, that we call it either armature voltage or supply voltage. So let me show you after solving it. You would appreciate it. Like it is correct what I am saying. VT is armature voltage. Once I will finish with this problem, you see, okay? Then if any doubt is there, you can ask. Fine?
yes.
Yeah. So E1 would be VT minus IA IA1 RA, I would say, because what would be the current flowing in first case? So it is saying that earlier the armature current was 10 ampere. I hope you are able to follow the problem. So here armature current was 10 ampere when fan was driving 1000 RPM. Okay, so at 1000 RPM, it was 10 ampere. So this is 10. RA was 1 ohm, I guess. So RA is 1 ohm. VT was 100 volt. So it would be 90 volt. This is E1. We calculated E1. We know the speed across it was 1000 RPM. Okay. When this armature was rotating at 1000 RPM, it was developing 90 volt. Okay. In second case, we know the speed is 500 RPM. Then what would be the back EMF and current if we can somehow if we can calculate back EMF in that case and current, armature current, then we will be able to calculate the armature voltage or supply voltage. Okay. So another information is given about the torque. Torque is given as N square. And since we know from the concept of DC motor or machine, it is proportional to pi Ia. And since a speed is reducing, it is not increasing from rated speed, right? It is reducing from 1000 RPM to 500 RPM. So it is still in constant torque region. We are not doing field weakening, so flux will still be constant. So it will be constant. So effectively, we can say the speed square is proportional to Ia. Now, we can write it as like that n1 square divided by n2 square is proportional to Ia1 by I. I hope it is fine till now. We know N1, we know N2. N2 is reducing to 500 RPM. We know Ia1. We can calculate Ia2. Fine. So I will do it. And Ia2 will be equal to Ia1 into N2 by N1 square. Ia1 was 10 ampere into a speed reduced was 500 RPM, a speed earlier was 1000 RPM, and I am doing here a square, so it would be 2.5 ampere. Okay. Ia2 we calculated. Now we need to calculate back EMF, right? E2 by E1 would be equal to N2 by N1. We are again ignoring flux since it is rated, so it will be constant. Even if you take phi 2 by phi 1, it is same, so it will cross out. Okay. So for that purpose, I will calculate E2, which will be equal to E1 into N2 by N1. And E1 we calculated, it was 90 volt. So 90 into a speed when it was reduced 500 divided by 1000. So it would come out to be 45 volt. So we completed our both the objective to calculate current, armature current, and back EMF at the speed of 500 RPM. So at 500 RPM, now we need to calculate our armature voltage. So armature voltage would not be equal to back EMF. Why? Because now we need how much voltage we should apply so that the motor would run at this 500 RPM. Okay. So at 500 RPM, its induced EMF would drop up to 45 voltage. But our rated voltage was 100 volt, right? So if we leave our rated armature voltage at 100 volt and this 45 volt is reduced due to a speed, then current would flow would be 100 minus 45 by 1, that would be 55 ampere, and that is 5.5 times of rated current, which will not be acceptable. You got it, Anwar? Why we are calling it or why we are managing armature voltage? Because that's where we have the control. We do not have control on induced EMF because that will be dependent on a speed only. So for that purpose, we need control on supply side. And that's why it is asking how much, what is, how much armature voltage will be applied so that this motor speed will be reduced to 500 RPM. Okay. Is it fine, Anubhav? Yeah, fine. Thanks. So now, so this is not answer. This is not answer. This I was explaining. So at 500 RPM, I need armature voltage or terminal voltage, which I call. So it's VT2, let me call it, is equal to E2 plus IA2 into RA. And E2 we calculated 45 volt plus IA2 we calculated it's come out to be 2.5 ampere. So this is IA2 2.5 into 1, so which will be equal to 47.5. So this will be your answer, how much armature voltage you can apply. So any doubt in this problem? So I will summarize it once again. In the problem, it was asked that the load torque is of the characteristics of fan and it is varying with the square of the rotor speed. Earlier, the rated condition was given. Rated voltage was 100 volt. Fan speed was 1000 RPM, or the motor which was driving the fan, its rated speed was 1000 RPM, and its rated armature current was 10 ampere. This is a separately excited DC motor. Now the armature resistance was also given. To reduce the speed from 1000 RPM to 500 RPM, what was the voltage we can apply? For that purpose, I did all the derivations and I showed you that how to calculate this type of problem. So I hope no doubt in this problem. If any, you can ask me. So if no any doubt in this problem, let me go ahead and solve some other problem as well. So this problem is very simple because transformer is very simple machine. It is a static machine. So you do not need to worry about all the speeds and all. But still, it is a very important topic from gate perspective.
Solve how yes, one angle 90 degrees. Option is
Acha, acha, great, great, thanks. This you are saying it is the option. Okay. So let me solve it for others. Okay. And if you have solved, so you can revise it.
very MMF balance equations.
Yeah, yeah. In any equation or even transformation ratio you can apply, right? Or MMF balance equation is, in other terms, it is a transformation ratio. So we all know like E2 by E1 is equal to N2 by N1. Okay. In transformer, this is generally the trend which follow any transformer. And if E2 by E1, then I1 by I2. So this is famous transformation ratio, which you should keep in your mind. Okay. So let me read the problem for you. A three-winding transformer is connected to an AC voltage source. Okay. Here it is source. This is AC voltage source. This one. The number of turns as follows. So this is N1. This is the first winding. N1, which is 100. N2 is 50 and N3 is 50. So there are, in secondary, two loads are connected through the supply. To connect two loads in from one supply, we need to connect in this fashion. Or for multiple loads, we can do in multiple turns. We can separate it into multiple turns and we can connect to the transformer. So the load current was in this winding N2 was 2 angle 30 degree. So this was the load current in this. And in third load, it means second load where I3 is denoted, it is taking the load of 2 angle 150 degree. Okay. So we need to calculate I1. Since all the currents is coming from your supply only, all the loads it is drawing from supply. So how much would be I1? So we can apply any superposition theorem as well. Like I1 is equal to, let me, transfer it to primary side. So it will be equal to, from transformation ratio, I2 into N2 by N1. This I1 is due to this load, second I2 current of load, and again the other one of due to I3, the I1 would be drawn from the supply would be equal to N3 by N1. Okay. Now you just need to solve it. So it would be equal to, let me solve it for you. So I1 is equal to I2 was 2 angle 30 into it is smaller. So 2 angle 30 into N2 by N1. N2 was 50, N1 was 100 plus due to I3 it was 2 angle 150. Again the turns ratio was 50 by 100. If anybody has any doubt, you can stop me in between. So it will be divided by, it will come out to be half. So it will become 1 angle 30 plus again it will become half. So 1 angle 150, right? So you can break it 1 into, cos 30 plus j sin 30 plus 1 into cos 150 plus j sin 150. In this manner, you can try to solve in GATE exams. So cos 30 would be root 3 by 2 plus j sin 30 would be 1 by 2. Again, 1 cos 150 would be minus root 3 by 2 and j sin 150 would be 1 by 2. So this would cancel each other and it will come out to be J1. And J1 we can write it as 1 angle 90 degree. So from all the options you can select that 1 angle 90 degree. It was the first option. So you can do. However, this problem was asked for 2 marks. So it you should do it very carefully. You should not lose your marks in this type of easy problems. So that was about this problem. Any doubt in this problem?
यस सर, मैं कंफ्यूज हो जाता हूँ सर। यहाँ पर जो सेकेंडरी साइड में जो डॉट है सर, जो कि डॉट से मेरा करंट निकल रहा है,
निकल
अगर उसी समय I3 जो है डॉट में करंट इंटर करेगा तो उस समय मेरा एमएफ बैलेंस कैसे होगा सर? वो कैसे?
see in transformer the general rule of thumb, if current is entering on one dot, if current is entering on one dot from one turns, let us say it is I1, it is entering from this turns. So it should leave from that dot where the load is connected. Right? So it should go on this fashion so that any transformer would supply to the load. And this is according to the Lenz law. What Lenz law says, if the cause or whatever the cause should oppose, no, the consequence, whatever the consequence should oppose the cause. Okay. So if this is creating flux in this manner, let us say this manner, so this have to link across the both the windings. So to link the fluxes, even in motors also, to link the fluxes, both should approach each other. Whatever the load requirement of current, that flux should approach this, whatever from the supply. Right? This is not parallel. This I am just denoting that the whatever the consequence or whatever the result should oppose the cause. Okay. So in any transformer, if you are seeing that any current is entering from one dot, it should leave another. Otherwise, what will happen? The flux generated from one side, second load, then in if the current will enter in this manner, then this load would be also of that sort of load which will generate flux. So both are generating flux, and there are nothing to absorb the flux, so it will be waste. Okay. So for that purpose, we just denote, and there are no any dots in any physical transformer. If you see any transformer, there will not be any dots. You just see there are some connections, certain connections, windings. So we put dots for our convenience only, right? So is it fine, Abhishek?
यस सर।
Okay.
मतलब जहाँ भी होल्ड होए वहाँ पर मेरा डॉट से करंट हमेशा ये निकलेगा ही।
हाँ, एक से निकलेगा, एक से इंटर करेगा।
यस। अगर सपोज करते हैं जैसे कि वही डॉट नीचे रहता है जो I3 है, I3 के पास जो डॉट है वो डॉट मेरा नीचे रहता है, तो उसमें सिर्फ I3 की जगह -I3 कर देते हैं।
-I3, या -I3 होता है, माइनस। Okay, so I hope this session you would have enjoyed. So any question or any doubt till till to the point, or in this class, if you have any doubt or any suggestion or feedback you want to give, please go ahead.
इन नेक्स्ट सेशन सर ट्रांसफार्मर का क्वेश्चन
Yeah, sure. You have my mail ID. I shared
यस
my. So you send me that problem, and I will try to cover, parallel operation of transformer, where how much loading is required. So I will try to cover that topic. Okay. So,
ओके
you just mail me that question so that I will be specific to that question as well, along with the basic concept of that topic.
एक बार फिर से अपना ईमेल लिख देते हैं सर, वो तो स्क्रीन लिए हुए तो इधर आगे
Okay,
पीछे
okay. I am typing my email here.
थैंक यू।
Welcome. So, like, you guys are interested in machines or power electronics more? Which domain you like? You can tell me.
आई मशीन से।
Okay. So, okay, Anuva, both. Great. You should like because without power electronics, machine is nothing. So any electric motors nowadays that operates on your battery DC supply, and we all know to operate any motors we need AC supply, and to convert from DC to AC we need an inverter. And even if you need some, some other level of voltage, you again need some DC to DC converter. So you should appreciate both the subject. All subjects are important, and especially for GATE, in GATE you will be a lot of subjects, so you should prepare each subject. So actually, I'm not planning to take any further question.